Let's talk about automatic differentiation. There are multiple different terms that are used to refer to this. Also AD, algorithmic differentiation, computational differentiation, auto differentiation, or simply autodiff. And this automatic differentiation refers to a set of techniques to numerically evaluate the derivative of a function specified by a computer program. There are two alternative ways to compute differentiation, and automatic differentiation, how it is used nowadays, is different from both of these traditional techniques. Symbolic differentiation, the first of these two techniques, is what you might do using some mathematical software like Mathematica, where you input some function and then as output you get often a very long symbolic expression for the derivative. Also, that's what you typically do when you're asked to compute derivatives with pen and paper in school or during undergrad. And then, by contrast, numerical differentiation using finite differences, you would pretty much try out what the sensitivity to the output is with respect to different inputs. And while in the mathematical definition of the derivative, you kind of expect it to perturb the input by some infinitesimal delta that then goes towards zero. In numeric differentiation, what you say is, well, let's pick some delta that's pretty small, but not too small. Otherwise, there's even more numerical problems. So there's some trade-off. Maybe the smaller, the more problems. The bigger, the less accurate it gets. And so you can just, you have your program. You can perturb the input, maybe one input at a time. You perturb a bit and then see how the output changes, and you record it, and you perturb another input, see how the output changes, record it, and so on. So for this autodiff that we're going to look at, there are going to be two possibilities how we could do it in principle: forward and backward accumulation, and backward accumulation will be the winning strategy. Let's look at the motivating example why this is the case. We'll have a function that takes as input a vector x and as output produces a vector y. And it's this nested function, so we'll first apply h to x, then g to the intermediate output, and then f to this intermediate output. So we'll also can call x as w1, and then with this notation we'll have all the consistent naming scheme when we also call y w4. So we'll just use these two naming schemes interchangeably in the following. And alright, so the input is w1 or x, and it has n1 components, so dimensionality is n1. And then w2, the first intermediate output, is computed by h of the input x or w1. And then the second intermediate output, w3, is computed by g of the first intermediate output. And the final output, y or w4, is computed of f of w3. And w4 has n4 components, so w3 has an n3 components, and w2 has n2 components. Let's look at the derivatives in using a figure that depicts this function. All right, this is just the figure of what we saw before. This is now, maybe just think of it as your mini network, and win is the input that is processed by function h, then output is w2 that goes into function g, out comes w3 that goes into function h, and out comes y. So again, we'll use w4 interchangeably with y and w1 interchangeably with x. And so if you just look at this here, then here this f was on the outside, so f was way to the left and h was to the right, if we wrote it out as a nested function. And by contrast, if we're looking at the drawing as a graph, then we will see h occurring on the left side. H is closest to the input, and then f, the function f, or this graph node corresponding to the function f, will be way on the right side. Okay, so we see here h is going to be applied first, then g, and then f. And again, the input-output, so for example, h has n1 inputs and n2 outputs, then g has n2 inputs and then 3 outputs. And then what we know of the derivative, so if we want to compute the derivatives of these computational nodes, that means all the derivatives, so w partial w2 over partial w1, this will be a matrix, or there will be n1 times n2 individual derivative components. So again, for each possible output component in w2, we have partial this component over each possible component in w1. All right, so let's write this out using the chain rule. So the partial y partial x, that is, what is the sensitivity of the final output of this complete mini network, of this mini computational graph, with respect to the input x? Or using this w, the partial w4, partial w1, how does the output w4 depend on w1? And the chain rule says, okay, this is partial w4 over partial w3, w3 over w2, and w2 over w1. So now each of these components here corresponds to one of these nodes in the computational graph. Let's write this maybe more explicitly. So w4 is the same as fw3. So I see there's some small error, so this should be g of w2 here, not just a 2. Okay, so either we can look at this equation here. Here, let's just look at this here for now. So this partial w3, partial w2, you can imagine this is a matrix of size that has n3 rows and n2 columns. And again, there's n2 times n3 elements. So this thing here is can be considerably large, especially if the input and output dimensions are already large. Let's think of one such a block as maybe a convolutional layer, where we have a tensor, or maybe this one here. We have a w1, let's say, is a tensor of, is describing an image that has resolution 1024 square, and it has RGB as channels, and then as output we have an image of the same resolution but with 64 channels. If we really write out this complete matrix of derivatives, that's no doubt going to be sparse. However, let's just look at how many individual entries in this matrix. Matrix is going to be 1024 to the power of 4 times 3 times 64. So this is going to be a huge matrix just for this one single computational node. And this matrix might already be too large to store in GPU memory. So when we look at this again, and we now imagine all these components to be matrices, then, or tensors, so we'll just write the notation in such a way that it's better if we only imagine these things to be either vectors or matrices. Then this whole thing is associative. So when we multiply this out, we can decide, do we start at the front or do we start at the back? So we could start maybe multiplying this first element with the second element, and then we get some result and we multiply this with the third element, or we start at the back, we take this, we multiply it with this element here, and then this result combined will multiply with this first derivative here. And as we will see, there will be a winning strategy, and the winning strategy will be to start at the left side here, and this left side in the equation corresponds to, let's call it the right side here in the graph. So starting with the derivative of this block here, how does W4 or Y depend on the input W3? This will be the winning strategy for neural networks. And why is that the case? We will repeat that later. That is because the final output of the network, the loss function, is only a single scalar. And therefore, the derivative of this last block will be only a vector, just assuming this input is a vector, and this will be a lot smaller than the general derivatives that we have to deal with when we think about maybe convolutional or fully connected layers. And because this part here is going to be, let's say, small in dimensions, then if we take this equation and start at this side and start accumulating from left to right, or if we look at the graph in the backward direction, we will have only small values that we have to compute, assuming that I don't explicitly form these derivative matrices, but I have some way to kind of compute this matrix free in a way that I don't have to create these very sparse large matrices, but I can encode efficiently, compute the basic vector matrix products. Okay, let's look at this forward accumulation and backward accumulation strategy. In forward accumulation, we proceed left to right in the graph. So we have this computational graph, and we would first look at the derivative here, and then we would accumulate by going in the direction of the output. So forward accumulation, we start at the input and we go in the direction of the output. In backward accumulation, we proceed right to left in the graph. We start at the output and work our way back to the input. So we would start here, and the first derivative to consider would be the derivative here, that is dy dw3. So for completeness, there are these recursive relations given here, and you can read a bit more about this on Wikipedia, for example, when you search for automatic differentiation. So this is now our key observation, that is, in the neural network, here, this N4, the final output, is only one-dimensional, and therefore backpropagation is a great choice. That means when we are now backpropagating derivatives / gradients, then we will only need data structures that are the same size as the data structures that are used to propagate information forward. Because we will look at these partial derivatives that have all the structure of partial derivative of, so we will look at dy with respect d3 first, and then dy, d2, dy, d1. And all of that is, these are all like blocks that have inputs that can be whatever, but the output will always be a scalar, and therefore these derivatives will have manageable size. So for example, if we look at the combined block here of g and h, we could think of this as like a black box function that has input w2 and output y, and looking at the partial derivatives of w2 of y with respect to w2, we are again in the case where we only have a single output and however many inputs, but then that means the derivative will have as many components as w2 has components. Okay, that's great so far, but of course there's a catch. The problem is that we will have to make a complete forward pass before we can start the backward pass. And in the forward pass, per default, we have to store a lot of intermediate information because we need the intermediate values from the forward pass to evaluate the derivatives. So that means we might have to store, let's just say, maybe the output of each, something like the output of each function. So we will, in the code, you can explicitly store something or not, and there will be some slight variations to that. But in principle, you have to think that you have to store a lot of intermediate values to make that possible. And the problem is you need to store for every sample in the batch kind of intermediate values for every layer in the network. And that is quite memory consuming. Therefore, deep learning, training neural networks, is a memory intensive endeavor, and memory is very often a limiting issue when you want to train neural networks. Also, as a remark, if you're thinking of some other type of computational graph, not a neural network, but some computation where the input would only be a scalar, and maybe you have a lot of different outputs. You could think of it as maybe some very complex building that has one single material parameter, and then you would like to know something about the stability or so of this building. Then you could imagine that forward accumulation is the right choice, because in this case the structure of the derivatives will be such that the first derivative will not have a lot of components, and so starting to accumulate from here, going in the other direction, where you always look at derivatives of some blocks or sub-blocks, so that are, maybe you look at this sub-block here, you want to know what is the derivative of W3 with respect to the input, and then the input always being a scalar. This makes the forward accumulation a good choice. So we'll look at some examples from the Stanford course. As a reminder, we'll use this type of notation, usually partial loss, partial sum value in the graph. And again, we'll look at values that travel on the edges of the graph. They can be shaped as whatever they are, but if then actual computation happens, it might help to think of actually reshaping the inputs and outputs so that they're always vectors, where then we have a Jacobian matrix that describes the derivative of a particular node. All right. Again, so if we have a neural network, the neural network describes a function that has n inputs and m outputs, and then if we look at the network plus the loss, then m will be 1. The network function depends on the input samples, for example the images, as well as the network weights. So we discussed all these different notations before, but since the function of the network depends not only on the network weights, but both on the input samples and the weights, there different types of gradients, derivatives we can compute. We can compute derivative gradient with respect to the network weights, and we can compute derivatives with respect to the input samples, or both. I could ask, what is the sensitivity of the loss function with respect to the network parameters? But I could also ask, what is the sensitivity of the loss function with respect to the input samples? I could ask, which pixel in the input image to change such that the loss gets smaller? I could ask, maybe, to change an image to make it look more like an elephant in a texture, in an image classification context. So, you know, we might want to compute typically during training. It will be very important to compute derivatives gradients with respect to the weights, and for certain adversarial attacks, style transfer type of applications, we see often that we want to compute derivatives with respect to the input samples, the input images. Right, so that since we're using gradient and derivative interchangeable, you will see a lot of this notation that just involves the gradient. And just a reminder, the gradient, if you write the subscript something, that means you compute the gradient with respect to these values. So for example, gradient symbol subscript vector w of this function fxw means you compute the gradient with respect to these elements of the function. So with respect to the parameters w. All right, then as a last part of the network, again, we'll have this loss function, and the loss function has only one output, which is the key reason why we choose backward accumulation, backpropagation. So we mentioned this before, and so when we look at the loss of the network, we have to be careful that it's not really only like this graph that's only a path and then the loss is the last node. The loss can have basically inputs from all over the network. So all network weights are often connected to the loss, and there could be side branches computing some auxiliary terms that also contribute to the loss. So if you imagine this loss, it helps to really think of, you know, connections from everywhere within the network being formed to this loss computational node. So the loss affects kind of almost the complete network simultaneously. All right, so here's maybe a simple example network that has a linear layer L1, a ReLU layer L2, and another linear layer L3. So the network output would be S equals this network function, which is matrix W2 times max 0, and here matrix W1 times X. So W1 times X is the first layer, max 0, and that is the second layer, and then W2 times this is the third layer. Then we would use weight decay, where we have as regularizer, where we have the regularizer on both the weights of W1 and W2. So this W is just a simplified notation that contains both W1 and W2. So we have the parameters of this layer and this layer connected to the loss as well. Then we have data loss. Maybe this is a SVM or hinge loss. So the total loss would be the data loss and the regularizer. And so what we then would like to do when we optimize is we would like to know what is the derivative of the loss with respect to the parameters of the first layer, and what is the derivative of the loss with respect to parameters of the third layer. So we want to know the derivative of the loss with respect to this group of parameters and the loss derivative of the loss with respect to this group of parameters. All right. So this gradient, or all these gradients derivatives, are difficult, tedious to compute by hand. It is difficult, if you do that by hand, to change components of the network if the gradient has to be recomputed in code every time. This gives rise to many copy-paste errors and many opportunities to forget changing the code. And since the loss function really includes kind of components from all over the network, this might actually be quite difficult to write. And the network itself, this is maybe a point that's missing here, can be very, very complex. So we'll see at the end there will not only be this very simple linear path type of networks. These networks can look like arbitrarily, insanely difficult graphs. And this is just really difficult to handle if one would embark on explicitly writing code for the derivatives. So what we would like is to have a software infrastructure that handles these computational graphs in such a way that we have to implement as little as possible, and that we have to that we have as few possibilities to make mistakes as possible. So this was kind of the example, not totally, but similar to the example before. Maybe there's a mini computational graph. We see that here's some type of linear layer, then there's a loss, there's a regularizer that gets then added and fed into the final loss that combines the data loss here and the regularizer loss here. Also some other drawing. This is AlexNet. So then these are the layers that would all have parameters that contribute to weights. Here's the image, input image, and then there would be a final loss layer. And for something like this, maybe you could imagine still writing the derivatives gradients, but if we look at some other networks, this can be a lot more difficult. So for example, this paper from 2019 explores randomly wired networks. And as you can see here in these examples in figure 1, this can already look quite ugly. Maybe go to the end. There might be some other networks. And you know, you can imagine it's not going to be a lot of fun to think about derivatives here, in the sense of having to write explicit code for these derivatives. So here we can see the backpropagation algorithm from the point of view of one node that has scalar inputs x and y and a scalar output z. This will be very similar when we are generalizing these two inputs that can be other types of tensors, mainly vectors, but these tensors could also be matrices or higher rank tensors that can be processed pretty much in an analogous way. So the data in the forward path that travels along the green arrows, so this scalar x would travel along the green arrow. It comes from some node that's maybe further to the left, and it will be an input to f, and y also travels along this green arrow, and it's also another input to f. And the output is z, and in the forward path, z flows further upwards until it's going to reach the output of the complete network. And in the backward pass, the information is going to flow from the loss function of the network backwards towards the inputs of the network. So in the backward pass, the data will travel along these red arrows, and each green arrow has a corresponding red arrow, and when the green arrow carries the information of a variable or a tensor in the general case, so here we have the variable z, then the corresponding red arrow that carries the derivative of the loss function with respect to that variable. So the derivatives that we are dealing with are always going to have dl on top, and then on the bottom here you have dz. This will vary depending on which edge you're on, but it will always have the derivative of the loss function with respect to a variable. So we can double check that here. So here we see dl dy, and here you have dl dx. This is because we are doing backward accumulation of this automatic differentiation. Now, the equation that you kind of can remember here, this is the slightly reformulated way of the chain rule that is used in these drawings, is downstream gradient equals upstream gradient times local gradient. So to get the downstream gradient that travels backwards from a node, so these downstream gradients would be dl dx or dl dy. These would be composed of the upstream gradient, so the upstream gradient dl dz, this is what comes in here, this is what's also denoted as upstream gradient, times the local gradient. And the local gradient is the output, that is the derivative that is of the output variables of this local node with respect to the input variables. So if I'm interested in this red edge here, I'm interested in the derivative of z, the output of f, with respect to x, that is whatever traveled in along this green edge here. And then analogously, here we have the local gradient is dz dy. So that is dz, that is the output of this local node, derived with respect to the variables that come in along this green edge here. All right, so again, the chain rule is downstream gradient equals upstream gradient times local gradient. Also, as a review, what data travels along edges. So we have inputs x, we have the network weights, the network parameters, and we have the output of computations of intermediate nodes. And in the forward pass, we compute the values of intermediate nodes for each edge, and in the backward pass, we compute local gradients for each nodes. We compute a gradient basically for each edge using the chain rule. So if an edge has variable b in the forward pass, then in the backward pass we compute dl dv, that is the derivative of the loss with respect to this variable. Let's spend some time looking at examples. What we see here is a simple backpropagation example, and you see a computational graph that corresponds to this function f of x, y, z equals x plus y times z. So we break this down into individual nodes. So we have 3 inputs, x, y, and z. The first 2 inputs, x and y, get combined by this plus node here with intermediate output q, and q gets computed by x plus y. And then q gets combined with z with this computational node that computes the final output f, and f is z times q. So here we are kind of making up some arbitrary input and send it through the graph in a forward pass. So we'll say x is -2, y is 5, therefore q, which is plus, is 3, and z we say is -4. So in the end we obtain f -12, 3 times -4. Now we're gonna compute local gradients. Let's look at this plus node here. So how does q change with respect to this input y? So dq dy equals 1, computed by elementary calculus, and also dq dx equals 1. You can make a sanity check. You could think, okay, what happens if I increase y by some quantity? I increase this by delta, then q will also increase by delta. So it makes sense that the derivative would equal 1. So while the derivatives here are constants, this will change at this multiplication node. Again, to review elementary calculus, what is df dz in symbolic computation? So df dz equals q. By symmetry, df dq equals z. Let's again make a sanity check and look at this from the perspective of the value z and df dz. And df dz is q. So let's say q is a very large number. So q would be 1,000,000. So now changing z by a small amount delta, then this delta would get multiplied by 1,000,000 because q is so high. Now, in the other way, if q would be very, very small, so let's say 0.1 or 0.0001, then the delta would be multiplied with this very small number, and the output of z would, the z changing z would only marginally change the output. So even if we have some delta, then we multiply this delta with this number, so then the change in the output will be smaller than this delta that we use to modify z. But this was in some sense symbolic differentiation, just doing a symbolic differentiation of each of these nodes. What we're interested in is actually evaluating the gradients, the derivatives, at one particular point. And the particular point is the one that corresponds to the sample. So we want to have the derivative at the point that corresponds to exactly the inputs that we used in the forward pass. So in order to initialize the computation, we make the we create this base case that will start sending a derivative into the first node that is df df, and that is always 1. So basically for this last computational node in the graph, there is no upstream gradient. Therefore, we'll just set it to 1 by convention. I think that's somewhat helpful, and that's a good idea by the creators of the Stanford class where this example is taken from. So the equations are written out on the next slide. I'm just going to talk about it on this slide. And if you're interested, you can look at the equations in the lecture notes. So now we want to know what is traveling backwards along this edge. So what is this red number here? We said that df dz equals q, and now we look up the specific value of q that was coming into this node. So this specific value is 3. So the local gradient, the local derivative is 3, and the upstream gradient is 1, so we have 3 times 1 is 3. Now symmetrically, df dq equals z, and so we multiply this value here, -4, with the upstream gradient 1 here, and we obtain -4 that is traveling backwards along this edge. For the plus node, we observed that dq dx as well as dq dy equals 1. So now the local gradients for both of these edges are 1, and then multiplying 1 with the upstream gradient -4 gives us -4 in both cases. Again, looking at these input variables to this computational graph, x, y, and z, these numbers here tell us how sensitive the final output f is with respect to changes of these input variables. So let us assume we would like to make the output f smaller. The derivative or gradient tells us, so let's stick with the gradient idea. The gradient tells us which direction do I need to go to locally increase the function the most. So I want to go in the opposite direction. So if I want to make the output smaller, I would like to make z smaller. So maybe I would subtract -3. For y, it's different. So if I would like to make the function smaller, then I would want to make y bigger. And again, this is only locally true at this particular configuration where x, y, and z assume these 3 input values. For example, how to change z to decrease the function f. This is not always the same. It's not always we have to add or always we have to subtract. This will depend on the values that x and y assume. So while this is of course extremely trivial, we just want to explicitly state that the strategy for either increasing or decreasing the final output is not only local, so one cannot just look at one variable and decide what the best strategy is. It really depends on the local configuration on all the variables that are used to configure this network. Alright, so here's the computation I just talked about when looking at the last slide. So let's look at another example. We use this function that is 1 divided by 1 plus e to the power of an inner product between a function, between a vector x and a vector w, and then some bias term w2. We'll select some arbitrary input values to illustrate this functional graph, and we'll just look at it in the visualization. So first, we should be able to convince ourselves that this computation is indeed true. 2 times -1 is -2. Let's just check. -2 times -2 plus 6 is 4. That looks correct. And then, okay, 1 times -1 is -1. 1.37. 1 divided by x, 0.73. Kind of sounds reasonable at least. However, to check these numbers, you would need to use a calculator or a computer, because this e to the power of, or 1 divided by x, you need to be able to compute exactly. So if you do that, then you will see that these numbers are rounded. So here in this example, we'll look at the backpropagation algorithm. And again, we have everything are scalar values. So by convention, we say that the first upstream gradient here is always 1. Now, we'll have to look at this node here. There's one input, and then we want to compute upstream gradient times local gradient. So the derivative of 1 divided by x is 1 divided by x squared times minus 1. So minus 1 divided by x squared. Therefore, we need to take this value and we need to compute 1 or minus 1 divided by 1.37 squared times 1. And this gives minus 0.53. So I wrote all of this out in quite a lot of detail just so that you might be able to check later. And for the notation that I use here, I use these node names. I use them to name the output of a node as well as the function that the node computes. So looking at this node that is labeled f, we would say here this computes the function f, and as input it would take this variable that is also named f1, which is the output of this computational node that computes the function f1, but we also used it then to name the input variable of this node f. Okay, quickly, this is a +1, so the upstream gradient is routed straight through because the local gradient is 1. This node here computes e to the power of something, and what we have here is the upstream gradient is minus 0.53, and the local gradient is also e to the power of the input. All right, so e to the power of minus 1, we actually luckily know what it is. It's 0.37 because the forward pass computed exactly this number. So in order to get this red number minus 0.20, we need to multiply this value with this value, where this is coincidentally exactly the local gradient. All right, now times minus 1, that flips the sign, and with plus, we already said local gradients would be 1, so therefore this 0.2 travels backwards along this edge, as well as along this edge, plus same thing, local gradients are 1 for all the inputs, so this 0.2 travels now backwards along this edge as well as this edge. And from the first example, we should remember that how does this output of this node f7 change with respect to x1? Well, this depends on w1, so this is w1, the local gradient. So in order to get this minus 0.59, we compute 0.2 times minus 3. All right, let's look at some other one here. So how do we get this value here? This is computed by taking 0.2 times minus 1. This gives us minus 0.20. Okay, again, if you look at the course notes, this is a very excessively detailed description of the computation that we just discussed looking at the previous slide. All right, some more computation and some more computation. So this is just if you want to make sure you understood and you want to check later. All right. So the decomposition of a function into a computational graph is not unique. For example, you can take some of these very elementary nodes and combine them into a more powerful combined node. So if you look at a part of this computational graph before, this one here, this corresponds to the sigmoid function. Should we have computational nodes that correspond to something like a +1 and then e to the power of, or should we have a computational node that just has the sigmoid function as one single node? And the answer is that we need to choose nodes that are not too complicated so that the local gradients are easy to express. And in some cases, for example, the sigmoid function, we can compute the derivative analytically, and then we find out that actually the derivative of the sigmoid function is very simple. So again, sigmoid is 1 divided by 1 plus e to the power of minus x. I'm not going to do this derivation step by step, but in the end, we see that the function does look kind of ugly, but if we go and look back at how the original function sigmoid of x looks like, we can notice that the derivative is actually 1 minus sigmoid of x times sigmoid of x. This is a nice expression of the derivative. So we could imagine that this whole thing is now one single node where the derivative is computed like this. So the local gradient is computed like this, and then we would multiply that with the upstream gradient here. Okay, so how do we compute the local gradient? This whole thing computed sigmoid of x. So there was this thing coming in, and then sigmoid of x is actually this value here that we already computed. So the local gradient is 1 minus 0.73 times 0.73, and this is 0.2. And so we take this 0.2, multiply it with the upstream gradient, and then we also get the downstream gradient for this edge. If you look at the documentation of PyTorch, you can see that there are even some nodes that don't that seem to be almost computing too much combined together, because sometimes it is more stable and simpler to compute derivatives of functions combined together rather than keeping the functions separate. So we have, in some sense, the incentive to combine as much as possible, as long as we can still nicely compute the derivatives. What happens if we are excessively creating many individual nodes for trivial functions? As we discussed before, memory is a big problem of the backpropagation algorithm. This will lead us to having to store and memorize a lot of intermediate computations, and this is something we do want to avoid. So while in some sense this might be computationally equivalent, even though, as we said, it is not because of numeric issues, sometimes it might be better to combine nodes, even then the memory is going to be a big challenge. In this slide, we just look at some patterns that emerge if we look at how the gradients flowed in our network. So if we had a computational node that was an add function, then we saw that the gradient, the upstream gradient, in this case the 2, is simply replicated on all the input edges. So one could think of this as being a gradient distributor, or that copies the gradient on all incoming edges. We have a function here that replicates the input. Now this is often not explicitly drawn or I think we almost never drew it so far. When does this happen? So let's say we have a linear layer that has some network parameters W that influence this linear layer, but then these network parameters W, they will also be routed to the loss function. So in this case, we have these parameters W, and then they're copied once and sent to the loss function for the regularization, and once they will influence the linear layer, the network layer that they are kind of generated for. And actually these values could be used in different regularizers or different loss functions. So maybe we have the parameters, there's going to be an L2 loss, so maybe this could be a separate node, and then there could be an L1 loss, this could also be a separate node. So there's no limit how often these values can be copied. And so if you look at this, then the values, if they're used multiple times, we conceptually kind of have to think of having this copy gate. That means that this value 7 is now copied and sent to multiple other nodes in the network. And in the reverse direction, these gradients are being added. So maybe there's a 4 and a 2 being sent back. And so then on this edge backwards, we get 4 plus 2. Now, this is the multiplication node. And for the multiplication, we noted that we'll take this upstream gradient and multiply it with the input on the other edge. So if we are interested in the downstream gradient on this edge, we compute 5 times 3. Conversely, if we're interested in this, we compute it 2 times 5. So this is something like a swap multiplier, where we'll always multiply with the green value on the other edge and the upstream gradient. Now the max function that works like a gradient router. So there's an upstream gradient 9, and the gradient will only be sent backwards on the edge that actually wins the max function. So we have the maximum of 4 and 5, and this losing value 4 that is not considered by the max function, that will receive a 0. You can imagine that having this max function makes the gradient sparse, in the sense that there will be edges introduced that have a 0 gradient. So this is not very desirable, just thinking about gradient flow and how information is propagated, because when the gradient is 0, then it will not be possible to learn something for nodes and parameters further down when we go towards the input. And so having this max function, and maybe like ReLU has a max, for example, this has been linked in several cases to problems in learning. Now, again, a lot of this is conjecture, but when you visualize things, these sparse gradient patterns can be observed, and then there are certain artifacts happen that seem to be directly linked to such sparsification of the gradient. Okay, just text what we already discussed. Just the reminder here, so if f is max x1, x2, then df dx1 is x1 greater equals to x2, and this notation is the Iverson bracket, and it evaluates to 1 if the condition is true and 0 otherwise. So if x1 greater equals to x2, this Iverson bracket evaluates to 1. While not really recommended, we could try and go ahead and write out the code explicitly to compute the gradient flow in this example network. So if we do that, then we would see that the gradient flow seems to be kind of mechanically linked to what we compute in the forward pass. So we have these input variables. Let's just go back and check what they are. W0, X0, W1, X1, W2. So what we have is intermediate computations S0 to S3 by relying on these input variables. Then S2 is combining two intermediate computations. S3 is combining one input and one intermediate computation. And then the final loss is a sigmoid of S3. So what we're going to implement is what we discussed before, this idea applying the chain rule by always multiplying the upstream gradient with the local gradient. So we just initialize by saying that grad L equals 1. So that's what will be used in the first node. Now, it's not like strictly necessary to set it, but I like to stick to this kind of scheme, because since it's 1, you can kind of omit it. All right. So then we move backwards, and so the code works for computing the gradients works kind of backwards in the forward pass. So what we had in the forward pass, we had these lines 2 to 6 that kind of compute the output of the intermediates or the final node. And now we go backwards kind of line by line and always think about the gradient. So we had this line 6, and then in line 9 we compute the gradient for 6. So next we're going to compute the gradient for S3, and we'll just name it grad underscore S3, and this is grad L times 1 minus L minus L. Again, you notice the explicit derivative equation for the gradient for the sigmoid function. All right, and then we have the question, what is the gradient of W2 and what is the gradient of S2? And so again, working our way backwards in this code, we compute grad W2 and grad S2 here. All right, and then this goes on until the end. So for this simple example, this works out quite nicely, and you can do it by hand. Now, to scale this up, as discussed, we would like to have some code structure where these nodes can be kind of coded individually, and then hopefully PyTorch will be able to do the backpropagation for us without us having to do too much explicit computation. So one idea here that you see on this slide is we have just some arbitrary computational node, but in the code we would like to say what happens in the forward pass and what happens in the backward pass. So in the forward pass, there are two things that you need to do, and one we know about, which is trivial, which is to compute the output of the function. For example, z equals x times y. Now, because we have to do this backpropagation, and we said that one downside of backpropagation is that we need to store values, you see, in addition to the computation in the forward pass, we have to have code to store values that we need to evaluate the derivatives. And this is the line of code that corresponds to storing intermediate values that we need for this backward pass. Now then, you see this backward that then takes as input some upstream gradient, and it takes as input the CTX, which is used to store some intermediate values from the forward pass. And so then in this computation, you can see that we first access this storage CTX to get the values back that we stored, and then the computation of the downstream gradients using the stored values and the upstream gradient. While the PyTorch code is more complicated, you could still, and this is recommended as something to do, go and look at it and try to find some of this structure. So the computation itself will often be referred to some highly optimized numeric libraries. So you might not see all the computation there, just a call to some other library. But let's look at something that we could recognize here. So, for example, this type of computation is just like recursively chasing you. So you have to chase down where actually the computation happens. So let's say if we see something. So for example, this one here, this looks like a familiar line because this is the pattern that we identified to actually compute the derivative of a sigmoid. So again, I will make a break here in order that these recorded lectures are not too long.